When you write a function, the type signature enforces a lot. The types of the arguments, how many there are, what comes back. If you get any of that wrong, the compiler catches it. Of course, the degree of enforcement and whether or not it even happens depends on the language, but the idea is there. But when two processes are communicating with each other, we don't really have that. Both sides just have to agree on what gets sent, in what order. And if someone gets it wrong, you find out at runtime, or worse, things just silently deadlock. Which seems strange because it feels like it should be possible to have that same kind of enforcement. And it turns out it is. There's this idea called session types, where the type itself describes the entire conversation, and if both sides type check, they cannot deadlock. So let's see what that actually looks like. So what actually is a session type? Well, it's a type that describes a protocol from one side's perspective. Let's say you have a type that says to send an integer and receive a boolean, then end. With session types, after you send that integer, you don't just still have the same channel. The send operation consumes your channel and gives you back a new one with a different type. Now it says receive bool, then end. Which means you literally can't send again. The channel that allowed sending is now closed. You now have a new channel that only lets you receive. If you try to send something again, it will prevent you from doing it. And you can imagine exactly how this would be useful to prevent unwanted behavior. This is pretty different from how we usually think about channels or sockets. Conventionally, a channel is just a pipe. You can send or receive whenever you want, more or less. But with session types, the type itself changes as the conversation goes, and at every step, it tells you exactly what you're allowed to do right now. Now comes branching. If the protocol branches, like the other side might say ready or busy, then the type branches too. You wait to see which path they picked, and your channel narrows to that branch. So if you got ready, you're now holding a channel typed for what comes after ready. You can't accidentally handle the wrong case. This is somewhat inspired from something called linear logic. So in classical logic, the kind you might have learned earlier in school, once you prove something, you can use it forever. A implies B, you know A, so you get B, and you can still use A again for something else. Facts don't get used up. In linear logic, introduced by Girard in the 80s, each fact is a resource. For example, you have A, you use it to get B, but now A is consumed. You can't use it twice. This is not a video about linear logic, so I'm not going to go into the details, nor am I the best person to even explain it, but we can move forward just with that understanding. What we just established about linear logic might sound like an arbitrary restriction, but it actually models a lot of things we deal with on a daily basis, things that get used up. A message in a buffer, once you read it, it's gone. A file handle, once you close it, can't close it again, etc. Session types essentially inherit this. Your channel is a linear resource, so when you send or receive or branch, you consume it and get back a new one with a new type. And now that old channel is gone from your program, enforced by the type system. And this linearity is what makes the guarantees about types work. You can't forget to finish the protocol, for example, you'd still be holding a channel that demands more steps, and the type checker complains. This might remind you of the borrow checker, which does something similar. Values that have been moved can't be used again. Session types take that same idea and apply it to communication. There's actually a session types library for Rust that leans on the borrow checker to do the enforcement as far as I know. Though Rust's type system is technically affine, not linear, meaning you can use something at most once, but you're also allowed to just drop it. So the borrow checker alone can't fully prevent you from forgetting to finish a protocol. The library works around this, but it's not a pure compile time guarantee the way it would be in a language with true linear types. So far, we've been only talking about one side of the conversation. But, as we all know, a protocol has two parties. How exactly do session types handle that? Every session type has a dual. If your type says send an integer, the other side's type says receive an integer. If yours says receive, theirs says send. If yours says wait for a choice, theirs says make a choice. That's essentially what it boils down to. Now, think about what deadlock actually means. Both parties waiting for the other to do something. Both blocked on receive. Neither will ever send, right? But let's look at what duality gives us. If one side's type says receive, the dual says send. They can't both be at receive. The types literally don't allow that configuration. One is always ready to send while the other waits. So if both sides type check and their types are duals, and the runtime correctly wires the two endpoints together, deadlock is by definition impossible here. It is worth noting that while duality of types gives you the complementary structure, the system also has to ensure the two ends are actually connected. You need both. Once that's in place, though, the types rule out the state that causes deadlock. Now, I should be precise here. This clean guarantee holds for a single session between two parties. Multiple interleaved sessions or three or more parties, that gets more complicated. There's a whole field of multi-party session types for that. But the two-party case already covers a lot. Request-response, handshakes, negotiations. That is by no means trivial. So that is session types. Types for conversations, linear logic ensuring each step happens exactly once, and duality, keeping both sides in sync. It's worth asking what you give up. Not every protocol fits neatly. Keep sending until done needs recursive types. Protocols that depend on runtime values can get awkward to type, and sometimes you end up reshaping the protocol just to make it typable. There's also the practical side. Most languages simply don't have session types built in. You're either using a library with some friction or a research language that's not production ready yet. Having said that, even if you never use session types directly, the ideas change how you think. We're used to types describing what a value is, but session types describe what a value will do over time, across interactions, and the correspondence with linear logic is quite precise. Wadler's propositions as sessions makes it explicit. Protocols mirror proofs. Curry-Howard again, but for communication instead of computation. If you want to go further, Wadler's paper is the canonical reference, and there's Scribble, which lets you describe multi-party protocols and generates typed APIs. Session types have been around since the 90s, still not widely known, which is a shame. Well, I'm not sure about how to close this, but thank you for watching, I guess, and I would invite you to please consult the resources in the description. I trust you will find them invaluable.